Yeah. Okay. So welcome you all to today's SAAO Colloquium. And today we have Professor Ranjeev Misra from Inter-University Center for Astronomy and Astrophysics, which is known as IUCAA, which is in Pune. So today he is planning to talk about the novel road to observing black hole systems. So without wasting much time, I will invite Professor Ranjeev Misra to talk about his colloquium. Thank you.
Thank you, Sunil. I know it's been already 1.5 years or more since we are into this pandemic and we are doing all these talks on online modes. And I'm quite sure not a majority, maybe a good fraction of you like me are getting very seriously tired of this online things. It's always good to see whom you're talking to and meet people, and also to see whom you're listening to. And so this sometimes this most of the time these online meetings, online talks are not as enterprising as they were before. And I also understand that uh, it's 11 o'clock in South African time, and maybe just after my talk you will have lunch. So your minds will be under lunch, and my mind, which have, since we are in this about 3 hours ahead, is already into what we will do in the evening. Although these days the evening celebrations are much more subdued than what it used to be before, but still the mind is there. So the reason why I was giving this prelude is that I was wondering what to talk about today, and I thought that, and but despite all this problem about online and all, I did agree to Sunil's invitation to give this talk, and so collectively put at least a good fraction of you into the horrible online mode. And the reason I thought I'll talk about is, why are we doing this? I mean, despite all this trouble and associations with everything, we are continuing to do and working and exploring our universe. There has to be a very good reason for doing this and all. And so, what I will do today is not talk about any specific work of my own or anybody else's which I've been working with. Or I'm going to try and answer the question of why we are doing things, instead of telling you about what we are doing in the whole thing. And from the suggestion of my title, you would think that one of the good reasons for anybody to do science would be to, let's say, get a Nobel Prize. But that is such a low probability that that cannot be the real motivation for doing things. In fact, what I'll try to tell you is that it's generally conceived that the Nobel Prize is is a prize given to a, a single individual or a couple of individuals, but this is usually not correct. In fact, the Nobel Prize is a celebration of all people like us who are spending so much time and effort trying to uh, do this kind of research. And the question is, and it's a celebration for all of us in the world. And I'll try to show you why that is true in my talk. And the other primary reason here is, why the hell are we here doing all kinds of things, spending so many hours doing this? So to me, so since I cannot talk about motivation for everybody, I'm going to talk about the motivation for myself, and I'm going to talk about something which has fascinated me from very early days, and that is the word black holes. And I'll start with a little bit of telling you what black holes are there, and you know, and I would apologize for all the seniors in this audience, because my talk will be very pedantic. And but there is a reason for that, because I'm talking about motivation here and not really what we're doing in science. So let me start telling you what are black holes. And the way I do it is that uh, if you take the sun, and the sun is a very big object in the sky, and if you happen to squeeze it to a size of 1.5 kilometers, the sun is very, very big. But suppose you squeeze it, and you squeeze it to a size of 1.5 kilometers, by definition, that object which will form will be a black hole. So the first point I want to take home from you is that black holes are small and they're very dense in the thing. The because of even Newtonian gravity, that force which is gmm by r square, gravitational force is inversely proportional to r square. So if you take the sun and you're keeping the mass the same and you're decreasing radius, the gravitational force on the surface of such an object would be very, very high. And in fact, it would be very, very large, some this many times that of the Earth. So black holes have extremely powerful gravity, right? So uh, three factors: black holes are small and dense, and they're very powerful gravity. And they're called black holes because we understand that light cannot come out of a black hole. And I'll explain a little bit later. But the important thing here is that because we know light is the fastest thing in the universe, if light cannot come out of a black hole, nothing can come out of a black hole. And therefore, anything which happens inside a black hole will forever remain hidden from us. We will not know this. And so all the events which are happening in the universe, which are accessible to us, all happen outside the black hole. Hence, the surface of a black hole is called an event horizon. Horizon is something beyond which we cannot see. And the so the, whatever events so the events happen outside a black hole are the ones which are accessible to us. Now, an important aspect of black holes is that when light comes out of a black hole, it'll become redder in color, and let me explain a little bit on what that means. That means that if you are, let's say you're standing close to a black hole, but you're outside the black hole, and you shine a light to the outside wait, like you have a torch and you shine it out. Now, this light, as it comes out of a black hole, will lose energy, and as it loses energy, it become redder in color. Because, as we know, uh, the frequency of light is dependent on its energy. So the light has to work against the gravity of the black hole, and hence it gets redder in color as you. So if you are shown a blue light torch from a close to a black hole, a person outside will see it as red light. Now, if that person goes closer and closer to the black hole, not completely entering it, but keeps going closer, this redshift or this reddening will keep increasing till the point that when you come to the surface of the black hole, or which is called event horizon, this reddening is infinite. And that is the way in which we understand that light cannot come out of a black hole. Now, so it's not that light comes out and falls back, but this is the way by which we understand that light can never emit it, because any light coming from even from the near the surface of the event horizon would be reddened, and its wavelength will become infinite, and we will not be able to see it. In this talk, I'm only going to talk. This is the only thing I'm going to tell you about black holes, and nothing more on that, because there are a lot of fascinating things like how time and space gets inverted inside a black hole, which you can never know, or how space-time gets curved close to a black hole, what are the curvatures. We can do mathematical formulations on them, but that is not what I think is important. And so the question here is it an interesting thing to study black holes at all? And my feeling is that uh, when Einstein gave his theory of general relativity in 1918, and sometime soon after that, people like Karl Schwarzschild started developing equations which said that black holes exist. And black holes, what would happen if there are black holes? Not many people were very keenly interested in this topic. And the reason for why people were not very keen and interested in the concept of a black hole was the very reason how I started this talk. When I said that you take the sun and you squeeze it to about 1.5 kilometers in size. Now, how can that ever happen? Since that can never happen, it is not interesting thing to study. So black holes cannot form. You cannot never have something like the sun being squeezed to 1.5 kilometers. So what is the point of thinking and talking about things which may not, which will not exist? You know? So the first important question was, can black holes exist? And way earlier, uh, there was a young man who took a ship from India to England, and in that ship he calculated, he knew statistical physics and special relativity and quantum mechanics very well. So he did some calculations, theoretical calculations, and suggested the idea that under certain conditions, certain stars will indeed can collapse and form black holes. For this, Dr. S. Chandrasekhar got a Nobel Prize in 1983. So the fundamental thing he did was he answered this question: can black hole exist? With yes, there are physical mechanisms by which stars can collapse and form black holes. However, despite the statement that can black holes exist being answered, at least arguably, that there is a possibility, nobody is sure whether it was correct or not, but still, that again was not the most important question. The real, and which would have ignited interest in these objects, the real important question which is to be done was, do black holes exist? One has to distinguish, even, and sometimes these days people miss this out, that it is not always, these two questions are different. It's not always true that if an object can exist, it has to exist. There are a lot of things which do not exist which can exist, and an important aspect of science was to know whether black holes actually do black holes exist or not. So from now on, over the last 40, 50 years, we are now completely convinced, of course. The answer to this question is yes. We know black holes exist. And the story, or the partial story of how we came to know that black holes do exist, or at least I'm going to give you only a small part of the stories, is a fascinating one, I think. And also it gives us the motivation of why we do science as we do in our way. And what is the reason why we get motivated enough to do the science. So when you want to ask a question like, can black holes exist? You can go to your office and pick up a piece of paper and start calculating things, and 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 trying to derive things to answer a question like, can something exist? But when you want to ask a question like, do black holes exist? Then it's not papers or any calculation which can help you. You have to go there out and look. So since there are no black holes on Earth, we have to look for them outside the Earth. And my story begins in 1970s, I think, late 60s, when we got an image like this from the sky. This is a very old image. Look at the left side. This is an image of the sky taken from space, and a space which was looking at X-rays. You see, our Earth's atmosphere absorbs X-rays, so we cannot observe X-rays from the Earth. So that's why the story begins in the 1970s, when we had 60s, late 60s, when we had satellites, and we could go up and look at our universe in X-rays. And what we found was an amazing surprise. We found that there were many, many, many objects in our universe which were giving out X-rays. This was extreme surprise because we know that most of the objects in the sky, like the stars, the nearest stars around us, are so sufficiently far away that they should be very weak in X-rays. That means if you take our sun and put it in any of these distances, we would not have detected it in 1970s, the X-ray emissions. So it was extreme surprise that there are so many X-ray emitting objects in our universe. And for this profound discovery, which had a deep impact on our understanding of whether black holes exist or not, uh, the Nobel Prize for physics was given to Riccardo Giacconi for pioneering contributions, which led to discovery of cosmic X-ray sources. Uh, just to keep you in one day, remember, see this 30, 40 years lag between something being done and Nobel Prize being given. And that is because we want to be sure of how things happen and work it out. Okay. Now, coming back to this X-ray objects, there are two kinds of X-ray objects broadly, which I'll talk about. One are called X-ray binaries, which are these are source systems which are in our own galaxy. You see, we live in a galaxy which is uh, called the Milky Way, and from South Africa, of course, all of you can see it very, very beautifully. From India, we don't get to see the Milky Way so well, and that is been one of our great disappointments. But I'm sure all of you would have seen the Milky Way uh, in its in its full glory. Well, the Milky Way is our galaxy, as I was saying, and it consists of many stars. And there are some sources which are inside in our own galaxy, and they're called X-ray binaries. But before we come to what they are, let me tell you what is one of the important factors of X-ray. First of all, some of these sources have a luminosity, or they're putting out energy per second about 10,000 times that of the sun, right? They're very, very bright. So the question is, what could they be? They could be like a collection of large stars or a very big star in the whole things. On the other hand, what we find is that they are variable in milliseconds. That is, they vary in time scales of a millisecond. Now, this is extremely surprising. And let me explain a little bit about why in physics we consider that to be extremely surprising. Is that if you see a candle and there's a slight breeze, the candle will flicker. And this flickering of a candle happens on timescales of, let's say, a second. Like for half a second, it'll be like little dim, and then it'll become brighter and become dimmer again. So it's just the flickering of a candle typically can occur around a 1 second timescale. But if I told you that the sun will disappear in a second, you will know that that's absurd. You don't need no physics to do that. You will know that such big object like a sun cannot just disappear in a second. If you have a very big forest fire, then nothing can stop the forest fire from disappearing in a second. It takes a time for big objects to change, but for small objects can vary quickly. Because the speed of light is the maximum speed, we can put in a constraint we can put in a constraint in this size of a system, which can vary in a millisecond. So the constraint we put is that suppose the object is varying on a time delta t, uh, then its size must be less than the distance traveled by light, that is c times delta t. If we see an object which is varying on a millisecond, then this object must be less than 300 kilometers precise. There's a small caveat here by which this conclusion can be avoided. That is if the objects are moving at a very relativistic speed, but I will not come to that right now. Take this for action that if an object is varying on a millisecond time scale, their size must be less than 300 kilometers. If these two statements are true, we are come with a profound conclusion that we have an object which is about 10,000 times brighter than the sun, but yet its size is less than 300 kilometers. What possibly could such objects be? Let's take a look at one more kind of objects in the sky, which is called the active galactic nuclei. Now, our galaxy is just one galaxy of billions and billions of galaxies in the universe. And the centers of these galaxies in the of centers of some of these galaxies, about 1%, 2%, are very bright, and they are called active galactic nuclei. Now, just the center of these very bright galaxies can give out energies which are equivalent to 10 times that of the, or greater than, much greater than 10 times that of the whole galaxy uh, in the picture. But again, they're variable in timescales of minutes. And if you know that light takes about 8 minutes to come from the Earth to Sun, so we have these very, very bright objects in the sky, which is 10 times that of a galaxy. And a galaxy consists of 10 to the power of 11 stars. That is 10 to the power of 11 is about 1,000 billion stars. That means a galaxy is over 1,000 billion times more luminous than the sun. But this single central object in the center is variable in timescales of minutes, and hence the size must be less than the, the distance between Earth and Sun. So a compact object which is so small is producing more than 10,000 billion times the luminosity of the sun. So what are these possible objects which could produce such things? And one standard mode of doing this is by nuclear burning, in which you produce, if you have two hydrogen atoms and you fuse them together, you will produce energy. And this is the way by which hydrogen bombs work. And more importantly, this is the way broadly by which a sun gives out energy. And of course, it's a very efficient form of energy. But the most powerful source of energy in the universe, we now understand, is not fusion. It is actually something more common, that is similar to how we get hydroelectric power from having dams and what is gravity. You, if you are in a potential and you drop things, you will gain energy from it, kinetic energy, and this can be done. So in a thought experiment, suppose we take some particle and throw it close to a black hole. By the time it comes close to a black hole, it will be starting to get about 1/10 the rest mass energy of its object. So black holes with a strong gravity are powerful sources of energy in the universe. So we have an interesting situation here, is that if, apart from certain caveats, if you have followed me here, is that we observe objects in the sky which are very small and very bright. And we know hypothetically that there can exist some objects in the universe called black holes, which are very small and dense, but because of the strong gravity, they're very powerful. Hence, it is tempting to say that these objects are black holes. However, if any of you are interested in law, this is not real evidence which can be taken in a court of law. And because this is what they call circumstantial evidence. It is circumstantial in the sense that uh, you cannot find anything else which can do this, and hence you are saying that this is the truth. For example, if you find that a person A could have murdered person B, and I cannot think of anybody else who could have murdered person B, you cannot hold in a court of law that A is the killer. The same logic happens here. And so this is called circumstantial evidence, but there's a strong circumstantial evidence there. So let me go to a painting. And this is a painting of a black hole in the center. There's a tiny black hole in the center. There's a regular star going around this black hole, and matter falls from this regular star towards the object because they're very close to each other. And because this star is going around, it has angular momentum, and because it's angular momentum, it can go around. The matter goes in a kind of a circling around. If nothing else was happening, then this matter would have continued to go around circling the black hole just like the rings of Saturn. But since this gas is hot and viscous and magnetized, what it does is there is something called viscosity which happens, and viscosity is like friction, and this friction causes the matter to flow inwards and form something like a disk, which is called an accretion disk. Because friction and viscosity has produces heat, this accretion disk heats up, and by the time it comes very close to black hole, it produces a tremendous amount of it becomes so hot that it can produce X-rays, and this is the X-ray we are seeing. I went through that a little quickly because the two pointing I want to point out. First of all, that if you have not noticed that this is a painting, it's a drawing, it's somebody's imagination. We don't know whether this is really happening or the details of how this is happening. And in a real court of law, we should not let our imagination work. We should find evidences for them out there. One of the other evidences, how do we know that something like this is happening so far away in the universe at all? So we need more proof to show that black holes do exist in nature. So to do that, I show you a real image. This is a very old image of an HST image of a collection of gas in the center of a galaxy far away, going round and round and round. And we can see this ring, and by looking at this ring, we can make out that this collection of gas is going around a central object, which is probably very massive. This is after all an HST image, and during its time it was formed. It was one of the famous HST images. But to anybody else, it's not that spectacular. The evidence for this is very indirect. The main thing here was people wanted direct evidence, so they wanted to see whether we can actually see or find evidence for a black hole directly. The question is, why can't we look at a black hole? Why are we looking at galaxies which are so far away or small X-ray binaries? Why can't we look at the center of our own galaxy and detect what it and see if there's a black hole there or not? There are two reasons why this is difficult. One is that the universe is a dusty place. Our center of a galaxy is covered with dust, but you can use IR in imaging to do that. The second more is a stars twinkle. Stars twinkle because when light rays goes through our atmosphere, they refract and they cause turbulence. There is turbulence in the Earth's atmosphere, and this causes when we are looking at a star, a twinkling sensation. If you take a camera and see it, what it means is that the image is not always in one place. It keeps moving around, and as it keeps moving around, it gives you a final blurred image. Therefore, we had to go. Hubble Space Telescope was sent to space where there is no atmosphere, but it's very expensive to send a big telescope to space. So what people did was, and another I think one of the most finest and most sophisticated technologies ever in anything. The, uh, what you can do is you send a laser light to the top of the Earth atmosphere, form an artificial star, and study how the star moves around. And as it moves around, you try to correct your mirror to correct for this uh, variation of the star, and thereby get a very sharp image. All this is done in some millisecond time scales, and these mirrors, which are about 10 meters large mirrors like you have in the SAAO, the salt, are moved in nanometer slight, to get a perfect image. This is an amazing technology, but finally what people did in 1992 was, to me, one of the most amazing results is that they could get an image of the center of our own galaxy, and what they saw was nothing. I mean, this red spot is just a mark, but what you saw was 5 stars, but these 5 stars are normal, regular stars, garden variety. So the center of our own galaxy was a very boring place. There's nothing there to see. But what this happens is, if you they took photographs for many, many times, and when they did that, they saw that these stars are moving. It is not surprising that the stars move. Stars actually move in a way. But here the stars were moving in a very regular pattern. And if you had shown this to a person called Kepler about 300 years ago, he would have recognized what this is because he made the laws for them. Kepler said that planets should go around the sun in elliptical orbits. And here we have stars going down something else in an elliptical orbit. In my institute at IUCAA, we have school children who come to do some kind of a project with us, and 12, 13-year-old students who come in, who know a bit about physics and who are smarter. Many of them, we have given them this problem that, look at this star, this is how it is moving, this is the size of this ellipse, and this is the speed in which going. Can you tell me what is the mass of this object here? And they will correctly tell you that it is around 2 million solar masses. So for this, as we know, the Nobel Prize was given in 2020, again about the 30-year lag between the two, for the discovery of the supermassive compact object at the center of our galaxy. And that is, well, there is one problem with this image, is that we are not really seeing the galaxy. We're seeing the black hole. The black hole is still very, very tiny point out here in the center. So can we see and get more evidence for the black hole? Can we actually take a photograph? That's what we want, right? We want to see a photograph of a black hole. To image a black hole of a Milky Way, what we needed was a kind of an instrument which would have an angular resolution of 0.1 milliarcsecond. And let me remind you pedantically what a 0.1 milliarcsecond is quite impressive. That, you know, one circle is 360 degrees, but each degree you divide by 60, you get an arc minute. Each arc minute you divide by another 60, you get an arc second. You divide that by 1000, you get a milliarc second, and you divide it again by 10, you get a 0.1 milliarc second. And that kind of a angular resolution is required. And lo and behold, now using radio technologies, we can get it. And this was a simulation done by something called the Event Horizon Telescope Collaboration, which uh, uh, worked very hard for a long time to see if they can get an image. And this is what was released about a year and a half, 2 years ago. This is an image of our very nearby galaxy M82. And the black patch you see there is exactly what was predicted, or is not exactly, is what was predicted if you have a black hole and the black hole causes a shadow. So this is the closest evidence we have ever got that there is an event horizon and we're actually seeing an event horizon in the universe. Of course, this is kind of an old story now, and now we have much higher and better evidences for black holes, and the most amazing one was that of the gravitational wave detection. And the gravitational wave detection is done by laser interferometers, which are very large laser interferometers, and are very, very, very sensitive. So when far away, two black holes spiral against each other and merge, They give a ripple in space-time, which is just fluctuations in gravity. And these large interferometers can measure that. And finally, after many, many years of a lot of hard work and fine-tuning, such a gravitational wave thing was discovered. Now we have a large number of gravitational waves events which have been detected, and we now know that these are different kinds of black holes which are merging, and we and this pattern in which they're merging is completely consistent with the fact that these are black holes. In fact, two black holes merging in the center. So now there's no really question about how black holes. For this, again, the Nobel Prize in Physics was given in 2017 to Kipton for the discovery of black holes. So over this various time, we have been able to discover a lot of black holes, but the story doesn't end there. In fact, I would like to end my talk with the beginning of how we and most of my colleagues are doing research on. We have answered perhaps an important question that two black holes exist. But a fascinating thing about physics and especially our astronomy is not the questions that we have answered, but the questions we have not answered. And so let me start with something very, very interesting out here. Can you see this in this painting? There's this bluish little thing coming out from both ends. This in astronomy is called jets. With very little controversy, I can tell you, is that these are the most mysterious and unknown systems. What does that mean, mysterious? That if you ask people, how are jets produced? We will not get a good answer for that. In fact, there's some very speculation which have not been confirmed at all and probably not correct. If we ask questions, okay, what are jets made of? Even that we are not very sure. We think that jets are made of particles which are going around at very relativistic speeds. What kind of particles? Are they electron positrons, or are they hadrons, or the regular matter? We now think they're regular matter, but we are still not sure. There's so many mysteries out in this concept of jets that we do not understand them. But even before we do that, you see this object which is called the accretion disk, which is producing the uh, X-ray emission that I was talking about before. I also mentioned the fact that these objects are flickering in time. That is, they're varying in time. Yes, they do vary in time. But why are they varying in time? What is the nature of the variability? Why should matter close to a black hole vary in time at all? And often when we see this variation, we see them as flickering, and sometimes we see them as very regular oscillations. Why do they occur? What can we actually infer from them? We know that Einstein's theory tells us that time plays a very important part in Einstein's theory. And if we can measure variability and oscillation, we should be able to get to understand what Einstein's theory is all about. We are slowly, at this moment and over the many years, uncovering some of these mysteries and understanding them, but we are far from having a clearer pictures of them. We probably have to wait 30, 40 years more before we understand these things in our home. And to do this, what we have is a plethora of observatories which are in space, especially for X-ray space observatories. And these observatories are, and some future ones which will come up, will produce some hints and knowledge about what is happening in these black hole systems. So there's a combination of a large number of people required to not only analyze this data properly, and we also need people to be smart enough to figure out what this data means. And by then we would be able to get a little bit of better understanding and reframe our questions on what are black hole systems and why do they shine. Now that we have answered the question, do black holes exist? We are in time for the question of trying to find out what are black hole systems and what is the reason for their mysterious behavior in the same. So with that, I will stop it here. Thank you, and I'll leave you with this image.
Thanks a lot, Ranjeev. It was really very nice and simple talk for many of our students, and also it was really very good talk for people like us who want to do some outreach activities in near future.
Yes.
Yeah. So now
I would apologize for anybody who found it too pedantic, but I thought I will give this talk instead of my other talk on.
okay, yeah, great. Now we have plenty of time for questions. If anybody want to ask to Ranjeev, please raise your hand or write in the text box. Yeah, David.
Yes, Ranjeev, nice talk.
Yes, David.
Regarding the discovery of binary black holes, from the gravitational wave experiments, I think it's fair to say that it came as somewhat as a surprise to the community that there was this large population of very massive binary black hole systems. We knew about the smaller mass systems from what you've talked about, the fact that X-ray binaries manifested from, stellar mass, modest mass, I would say. But these binary black holes with 20 or 30 solar mass companions, or solar mass black holes, at the time I thought was fairly unpredicted. I just wondered if you had any comments on that, and whether you think that the theoretical simulations, our understanding of how to produce these has progressed from, say, 2015, when the first lot of binary black holes were being discovered by Virgo-LIGO system.
Yes, David, that's a very interesting question. I can tell you that a lot from my personal experience on this, anecdotal experience on this. Before the detection of this massive black hole binaries from the system, there were a lot of this work by Vicky Kalarga and others who had suggested that some of the most massive black holes that can form from experiment are 30 solar mass black holes. And I had always taken this number 30 to be a very sacred one. And I was like most other people, pretty certain that most black holes will fall in that range of 30 solar mass black holes. And I was, just to start, I was in Amsterdam when this discovery of the black holes, the first gravitational wave detection was happening. And I happened to be the privilege of being with Ed van den Heuvel, who was there. And if people remember, Ed has been one of those primary people on stellar evolution, on binary evolutions. And
yeah.
So even before the announcement came, we were waiting for the announcement to come live. I was talking to Ed and I said that, I asked Ed, will there be a surprise? That's the time when I realized that Ed already knew the result. He must have had inside information. He said, people will take it to be surprising, but I am not surprised. So he said, then I told him, but by the time the results came, I told him, but we had this idea that there were 30 solar masses. He said, no, that was, see, people write theories to fill in what they expect to see. So according to him, there was no physical limit of why they should not have been higher black hole masses, 50, 60 million. It's just that we are not seeing any of them, therefore most of the theoretical predictions were limited to that. So he didn't consider it. In fact, his hard upper limit on black hole formation was around 150 to 200 solar mass. So
Okay.
If anything above that, he would have put bets against anything above 120, 130. But till 70, 80, he was not very uncomfortable at all. In fact, that time it was 40 solar mass black holes. He was not uncomfortable with that at all. He said that's within the ballpark number. So, in other words, for much of the things we live and learn. So, as now we have now got a series of all these massive black holes, we have a much better theory understanding that these are not as surprising as they should be. But I guess we are still waiting for something like a 300 solar mass black hole to come up, where that would really, really put people in trouble, at least from binary evolution. Yes. And of course, if David, if some of our ULXS studies really work out, I still think some of them may be really. There are these ultra luminous X-ray sources which we see, which we are not sure what they are exactly. Now, many of them are thought to be neutron stars, but if a few of them do come out actually to be very massive black holes, that would be another important aspect on problems.
You're talking about intermediate mass there, right?
Yeah, I mean, no, even if we get something like 300-400 solar mass black holes,
Yes.
yeah, that would be quite striking. But we don't know how to prove that rigorously, right?
Yeah.
Yeah, thanks, David, and thanks, Ranjeev. In fact, I was about to trigger that regime of breed up these black holes, because you covered stellar mass ones in your binaries, and these supermassive in AGNs. But yes, we do have a hint. I mean, I should not say that evidences, but we do have some hints, like there are intermediate black holes harbored in the center of some clusters. So can you comment on that? Can you put light on that?
Yeah. I thought, I don't know, they would be slightly better for this, but I thought that we do not have anything very seriously below 10 to the power 5 solar mass. I mean, that would be a little. I mean, there are hints that they could be. But the other interesting point is, which I think comes from cosmology point of view, that all these supermassive black holes, how did they originate in the first place? So, if the seed black hole there was in the order of 10 to the power 4, 10 to the power 5, 3, then we would have seen them. I mean, then obviously some of them would still be in that size. So if you take the m sigma relation and push it down to that level, you could get it to work there. But I don't know. Any direct evidence of anything below 10 to the power 5, I'm not quite seen that. There was another issue of having this very light black hole masses in the center of even galaxies and things, is that they would have to form at the center then, because then the dynamical friction time is not sufficient for them to fall into the center. So that could be another issue about why are they at the center, because then they would have to be formed in the center as such, or the galaxy would have to be formed around it.
Okay.
But we'll have to see. These are all speculative things. I think apart from just one more point, apart from the fact that we are going to get a family of black holes in the whole location, I think there is still a lot of mysteries about what we already seen and know for sure. For example, jets and the time variability of black holes, which we don't understand at all.
Okay. So is there anybody else want to ask some question? Please unmute yourself. No? Then since many a significant portion of the audience work in either form of the black holes, so what I want, since you are here, so I wanted some of your comments related to this. First thing, generalization of accretion flow in various type of black holes, like a stellar mass or the supermassive ones? Can we have a generalized picture of accretion flow in all those black holes? And second, your comment, I want generalization of existence of corona in these black holes, because in case of stellar mass black holes, we do have like there is a very mysterious way to assume like there is a corona sitting on top of a black hole, and we don't know how it is stabilized over there, and we call it like it's like a jumping monkey over there. So yeah, we want comment on these 2 points.
Yeah,
Please.
okay. Let me get slightly more technical in this and tell you my feeling. You see, again, since I'm right now give this talk slightly in a historical perspective, let me try to remind people how all this history of this thing started, and that we should not forget at one point. You see, by the Shakara-Sunyaev model, which came out, if I had another talk which I could have given on that one, would have been that Shakara-Sunyaev 1973 paper is a 72, I think, paper is a standard thing about accretion disk theory. But that's quite a wrong thing to say, because it's only one small section of the Shakara-Sunyaev paper which is the standard accretion disk theory. In that paper itself, there was a lot of talk about what different kinds of accretion flows can take place and all that. However, at that time, they were limited in observational evidences for doing that and all. So what we know as the standard accretion disk theory is the first one which matches first with the observations which we are seeing, that is, of some black hole systems in the soft state. Very soon beyond that, we knew that there were hard X-ray emission coming from there. So one of the standard models for producing this hard X-ray emission came from this model called by Shapiro, Lightman, and Adley, which is a 2-temperature model. So people started developing theoretical models for that. But as time went by, then we had those Ramesh Narayan's advection dominated flows and adapt flows. Then we had controversies over all those flows and all. So, but the picture divided into 2 broad categories. One was a theoretical framework of actually developing how you can produce hard X-ray emission from a accretion disk. The second was a whole another school moved in by saying that let us assume that there is something like a corona or something, and then start working on looking at other features. For example, the reflection and other spectrum. So this idea of trying to infer the geometry of a corona from the spectrum and especially from reflection, all, in my opinion, has been getting a little too carried away. We really do not know the geometry that well, and things like what I call the lamppost geometry, that is, you just have a small spot of coronal hot gas lying on top of the accretion disk, is actually a mathematical simplicity and not reality. So we do have a lot of my worry right now, if you ask my more, is that there is a there's a divergence between theoretical solutions of accretion disk and observational features. It is fine when you're doing observations and doing analysis that you make approximations and say that this is like if you take a lamppost geometry or some simple geometry, that because you can calculate the spectra very easily there. But it's another thing to assert that your data is showing you this, that the geometry is like that. That is, I think, uncalled for. So if you ask my view again on this, I would say the verdict is out. We do not have the wherewithals right now to carefully predict the geometry as some people are claiming to be. In fact, a more important thing is to find out from real accretion disk theory is why should there be a hot corona at all? And we don't have a good answer to that question at all. I'm not sure whether I answered your question, Sunil, but this is the best I can offer right now.
Yeah, last week we had a very fantastic talk on a recent discovery by Dan Wilkins and et al. I mean, they have also predicted, like, they have used this lamppost geometry and modified it using for the disk reflection. And they say it, they say it like it's a kind of extensive complex model to predict the variability, which is driven by the photons which are coming from the behind of the black hole. So basically it's all assuming geometry in the core, that corona is existing and it's hot, it's signing the your disk. So yes, is still the advanced,
and it is very small.
Yeah.
The problem, the essential problem, I think, is the which Andy Fabian has tried to address in some, is the smallness of the corona.
Okay.
And you see, from the time when we were doing things, we had something called a compactness parameter, which is important. If you have a very small corona, you will have produce copious electron position pairs, and that can cause which will cause an instability runaway process. So therefore, we know people, but Andy Fabian is saying that they just stay in the realms of that. But the same point, that this is not coming from accretion-less theory, and that is a sad part. There is no theory which tells you that why there should be a corona hanging on the axis of the black hole like that, and that has causing a. Before all these theories were coming out, the standard picture was that the corona is an extended one surrounding a larger part of the disk, and I still don't see any strong evidence that it is not there. It is just some spectral fittings which are working on, and that's the problem. There is another interesting one. If you see that if you have a coronal source very close to a black hole, there is redshift, right? This is what I was talking about before. A huge amount of redshift which happens there. So the luminosity in the frame of the corona can be very, very high. And that again is the inconsistency in some of these models. So there is, I'm not criticizing them, I'm just saying that they're good. There's a way to go forward. But we should remember that there are lots of more questions to be that are unanswered. And that is how we need to figure them out first in the variety.
Okay, great. Yeah, thanks, Ranju. If
Thanks.
we have any other questions from audience? Okay, great. So this was really a very nice session, Ranju, and thanks for accepting our invitation. Thanks a lot.
Thanks.
Bye.
Thanks, Ranjeev. Bye.
Bye. Thanks. Bye.